Hi guys, I hope you're well. I'm going to have a look at the question I set for you yesterday and go through it in a little bit of detail about how to do better on these kind of questions again. Now, to be fair, it was quite challenging because we'd done a lot of the easier ones as we worked through the unit, so I had to kind of choose from a limited set. But that being said, it is very doable. So what I'm going to do here is I'm going to actually do this a little bit backwards. So the question's divided into two parts. There's a calculation section, and then there's some kind of definition and knowledge and understanding stuff. So the calculation is usually the meat of the marks in these questions, but in this case it's only 24, whereas the others are worth a total of 32. So let's start with these kind of easy ones first and work back into doing the calculation after. And the thing about the calculation is it's relatively straightforward, but you've got to be really careful about which values you use and just pay attention to detail on that. So let's deal with the part B first. Okay, name two processes by which a hot drink cools. This could be any hot drink, it doesn't necessarily have to be the one we're talking about today, but so a hot drink, how does it cool? Well, first, the methods it can lose heat by are it can evaporate. So evaporation is one. You can get air currents that come in and then take some of the heat away by convection. You can lose some by conduction, just to the surface of whatever it's on or to the outside environment. And you can also lose some by radiation. So there's four kind of processes you can lose heat by here. The three main ones and also evaporation. So how do you prevent each one? Okay, well if you want to prevent heat loss by evaporation, if you put a lid on it, you'll get less evaporation. You'll still get some evaporation, but you get less. At the same time, by doing that, you'll limit the amount you lose by convection because the air is trapped in here, so you don't have as much air to carry away the heat. Conduction, we use a styrofoam container, which has lots of little pockets of air that act as an insulator. And for radiation, the container usually has a bright colour inside, it's usually like white, which will reflect the radiation back inside the drink to minimise heat loss. So there you go, that's part B, boom, 2-3 minutes max. Now, I'm not writing each sentence out, but I'm just explaining it. Okay, speaking of which, a thermocouple is used to measure the temperature of the steam. How do you demonstrate the principle of operation of a thermocouple? Okay, thermocouple is just basically two different types of metal that are stuck together at the ends. I'm exaggerating a little bit here. And there's a voltmeter. So at the junctions, you'll get an EMF between those two. You'll get a voltage difference between the two junctions if they're at different temperatures. So what we do is we put one end into a beaker of water and we keep it cold, or at least we keep it constant. So we keep one end at a constant temperature and the other goes into whatever you're measuring. And what happens is you get an EMF, you get a voltage difference between the two, and that will depend on the temperature difference. So as the temperature difference increases, so does the voltmeter, and the voltmeter will detect that for us. So that's how the principle of operation of a thermocouple. Two different metals, one junction in cold, one other thing we're measuring, and an EMF across the two, which you can detect with a very sensitive voltmeter. Describe how to establish a calibration curve for a thermocouple. Okay, this might have thrown you a little bit, but we've done this experiment just in a slightly different spin. So when they say thermocouple, what you're really doing here is you're trying to establish how to use a thermocouple accurately, or how to calibrate it. Now we've done this experiment, but we did it where we had a thermometer that we knew about, like a mercury one, or actually it was an alcohol one, wasn't it, that we used. So we had an alcohol thermometer that we knew, and then we had an unknown mercury one, and we were trying to figure out how to use this as an actual thermometer. So the one that had measurements on, the one that was calibrated, and our unknown thermometer. And what we did is we put them into a beaker of water and gradually heated it up. I think every like 5 or 10 degrees Celsius, we recorded two things. We recorded what's the actual temperature on the known thermometer, and then we also had we put the other fella in. This time you'd be using a thermocouple. So you put a thermocouple in, and it's going to be the same idea. You plot the known against the unknown. So you plot the temperature on the known thermometer, so you could use mercury, you could use spirit, whichever, and then you plot that against the EMF difference, whatever the voltage difference the second thermometer gives you, because that's essentially what this is, remember, a thermometer. It's just using a different thermometric property. So you'd have the voltage in this scale, and then you just plot the two. That would be able to tell you then later on, if you wanted to use this on its own as a thermometer, you could, this has been calibrated now, so you could see what voltage corresponds to what temperature difference. Okay. So those two sections, pretty brief, and 32 marks out of the full 56. That's a kind of a good investment of time. Let's go back to the calculation. Now, the thing about the calculations are usually they'll be the lion's share of the marks. This time it was more of an even split. But Usually, if you're careful and methodical, you can get all of these marks, but it's very, very, very easy to make a mistake and slip up. So let's try and be careful as we go. Okay, let's get on to the meat of it. Let's get on to the calculation part. So it comes in two halves. We're going to do the top bit first. Then we'll come back to this one here. So the first time we're making a hot drink, steam's added at 100 degrees Celsius to 160 grams of milk at 20 degrees Celsius. If the final temperature you're looking for is 70, how much steam do you need? What they're really asking for is how much heat do you need to make this happen? Okay, so let's think about what's happening here. Whatever heat we add, that's the only source, sorry, beg your pardon, whatever steam we add, that's the source of heat. So whatever heat is lost by that steam, because that's the only source of heat we have in this, because there's no other loss to the environment, that's going to be equal to the heat gained by the drink, because that's the only place it can go. Okay, let's break down the steam first. So the steam needs to lose heat in two parts. The first thing it needs to do is lose some heat to condense together. So it's going to lose some heat as it condenses. That's the first one. It's also then going to need to cool down, because even after the steam's condensed together, it's still at 100 degrees Celsius. And we want it to get to 70, so it needs to cool from 100 to 70 degrees Celsius. So it will have to cool down. So the heat lost as the condensation, or the, essentially the steam, I misspelled condensation there, cools down. That's going to be equal to the temperature increase of the drink, because that's how it's going to manifest itself in the drink. Okay, let's kind of make this into an equation then. So we know most of this. We just have to be very careful about which values we use, because they've given us a load, and some of them we don't need quite yet. So they've given us the specific heat capacity of milk, aka how much energy you need to make the temperature of 1 kilogram of milk rise by 1 degree Celsius, by 1 Kelvin or 1 Celsius. And we have the specific capacity of the hot drink, 4.18 by 10 to the 3. Sorry, beg your pardon. Who cares? The heat capacity of water, 4.18 by 10 to the 3. And the heat capacity of the hot drink. I don't think we need that until the second part. They've also given us the specific latent heat of vaporization of water, which you do need. So again, they always give you what you need, and they don't give you anything you don't need. So we're going to need it at some point. Okay, so let's deal with this. Let's go back to the heat lost by the steam is equal to the heat gained by the drink. So the heat lost as the steam condenses plus the heat lost as it cools down is equal to the heat given to raise the temperature of the drink. So heat lost by steam as it condenses. We're going to use our first of our two equations. In that case, the heat lost as it condenses is the mass times the latent heat. The other equation we're going to need is that if something changes temperature, the heat needed to do that is equal to the mass of whatever you're talking about times its heat capacity, specific heat capacity, times the change in temperature, which can be either up or down. So heat lost by the steam as it condenses, well, that's the mass of steam. I'm going to use a little S subscript for steam, times the latent heat of vaporization of steam. That's the first one. That's given in the question. Plus the heat lost as it cools down. Well, that's the mass, again, of steam. I'm going to keep it as, I could say the mass of water, but for the sake of convenience, let's keep calling it the mass of steam. So the mass of the steam, now that it's cooled down to become a liquid, times the heat capacity of that steam, which is now water, so the heat capacity of water, times the temperature change. Now, let's think about this temperature change for a minute. This is cooled down, so it's going to be a delta theta which goes down. And let's think about like how much. It's gone from 100 degrees Celsius to 70. So it's gone down by 30k. I'm just putting one of those numbers in now to make it a little easier as we go. It's equal to, and let's do the same on this side, the temperature change of the drink is the mass of the milk. Let's use M for milk, because that's what we started with. They're putting steam into milk. It sounds bowdy, actually. It sounds disgusting. Mass of the milk times the heat capacity of the milk times the change in temperature of the milk. And the milk's gone from 20 up to 50. So its temperature change is upward by 50k. I'm just putting, you don't need, I'm just putting these in to explain how I'm going. So we have the mass of the steam times its latent heat of vaporization will give the heat loss as it condenses, plus the mass of that steam, again, now that it's cooled, times its heat capacity of water, times its temperature change. That's how much heat energy is lost altogether, will equal to the energy gain on the drink side of things, which is the mass of milk times the heat capacity of milk times 50k. Okay, let's do a little bit of algebra before we go any further. Let's kind of isolate what we're looking for. And what we're looking for is the mass of steam. So if you look at this side of the equation, both of these terms have mass of steam in them. So let's just take them out as a common factor. If I divide both of these in, put in brackets, steam, capacity of water times 30k, I can do that, that's cool. Is equal to leave the other side unchanged. And then Again, a little bit of algebra. We're looking for the mass of steam. Let's keep that on its own on this side of the equation and bring the rest across. So the mass of steam is equal to the mass of milk times the heat capacity of milk times 50k divided by, need to be careful here, the latent heat of steam plus heat capacity of water times 30k. Okay, I'm just going to go onto a new page, guys, if that's right, because I run out of room. In fact, I'm just going to start that fresh at the top. Ms is equal to CM 50k CW 30k. Okay, so let's plug in our numbers. We know the mass of milk is 0.16 kgs because it's 160 grams. So it's 0.16 kgs times the heat capacity of the milk, which is 3.90 by 10 to the 3 joules per kilogram per Kelvin. And we have to multiply that again by the temperature change, which is 50k. Then on the bottom half, we have the latent heat of vaporization of the water, which is 2.34 by 10 to the 6 joules per kilogram, plus the heat capacity of the water, which is 4.18 by 10 to the 3 joules per kilogram per Kelvin. I have to multiply that by the 30 Kelvin. Okay, we're getting there. Let's clean up the units a little bit before we put the numbers in. So on the top half, kilograms times kilogram to the minus 1 is going to cancel each other out. Kelvin to the minus 1 times Kelvin is going to cancel each other out. And let's deal with this side of the bottom half here. K by K to the minus 1 is going to cancel each other out. And then we have joules per kilogram plus joules per kilogram. So we're getting ahead of ourselves here a little bit. So let's deal with the top half first. So 0.16 times 3.9 times 10 to the 3 times 50. So for the top half, here I've got 31200. And in terms of units, it's just unitless. There's no units at the top. And let's deal with the bottom half. So let's multiply these out first. We have 4.18 by 10 to the 3 times 30, which is 125400. And we have that 2.34 by 10 to the 6 is still the same. Both units here are joules per kilogram. Joules per kilogram. Oh, I beg your pardon. It's not units up the top. Look, I've got that joules left there. Okay. So let's add bottom line plus 2.34. Let's put some brackets around so they don't get messy. By 10 to the 6. So I've got 31200 joules divided by 2465400 joules per kilogram. Okay, so 31200 divided by our answer from the last time, answer, SD to get it like not as a digital. So I've got 0.012655, and in terms of units, joules cancel each other out. We're dividing a number, we're dividing by K to the kilograms to the minus 1, so it's just kilograms. So 0.0126 kilos, otherwise known as 12.655 grams. Oof. Okay, there's the first half. Totally not easy, but doable. Very doable as long as you're straightforward. Okay, what's that? 10 minutes we're at so far for this calculation section, which is about on track. Okay, let's deal with the second part of the calculation questions. Let's just recap. A metal spoon is placed into the drink. Initial temperature of the metal spoon is 20 degrees Celsius, causing the temperature of that drink to drop by 68 degrees Celsius. What's the heat capacity of the spoon? You can ignore other possible heat transfers. The good news. Okay, apologies guys, I was interrupted there to kind of restart. So the second part, we're looking for, we've got a hot drink and a spoon is put inside, and because the spoon is cold compared to the drink, it's going to cool the whole mix down. So they ask, A metal spoon with initial temperature of 20 Celsius is added to the hot drink, causing the temperature of the hot drink to drop to 68. What's the heat capacity of the spoon? You could ignore other possible heat transfers. Okay, well this time, the source of heat is the drink. So whatever heat the drink loses, it's going to be used to warm up the spoon. It's going to be the heat gained by the spoon. Okay, so we have, on this side, the heat lost by the drink is going to be equal, again we're going to use Q is equal to M times heat capacity, specific heat capacity, times the temperature drop for this. On this side is a little different. The heat gain by the spoon, they're not looking for the specific heat capacity of the metal it's made from, they just want the heat capacity of the spoon. So that's just the heat capacity of the spoon times the temperature change. We don't need to worry about its mass because we're not given it. We're just looking for the heat capacity of the object as it heats up. Okay, so we have on this side the heat lost by the drink is the mass of the drink times the heat capacity of the drink times the temperature change. Now let's just think about the temperature change. It's gone from 70 down to 68. So that's 2 Kelvin. So you have the heat gain by the spoon, and that's the heat capacity of the spoon, which we don't know, times the temperature change, which we do. It's gone from 20 up to 68. So that's 48. Just check if my brain is working correctly. It is, yeah, 48K. Now let's think mass here of the drink, they're being a little bit sneaky, because if you remember the drink, we had 160 grams of water, and then we added around 12 grams of steam. So the whole drink is going to be about 172 grams. And in fact, let's be particular about it. It is, I had it done somewhere. Okay, let's just look back at our last answer. We got the mass of the steam was 12.655 grams. So the mass of the steam was 12.655 grams. The mass of the drink was 160. So the mass of the drink is 172.655 grams. But we want in kilos. So say that's 10 to the minus 3 kilograms. That's the mass of the drink. The heat capacity of the drink we're given in the question. 4.05 by 10 to the 3 joules per kilogram per Kelvin. That's this side. It's equal to the heat capacity of the spoon, which we don't know, times that temperature difference of 48K. Let's keep things simple. We want to keep what we want on one side, so let's divide both sides of the equation by 48K. So I'm just going to bring this across in essence. So let's just get rid of that and say that it's divided into this side. Okay, let's think about units before we go any further. We'll do the numbers in a minute. Kilogram by kilogram to the minus 1, that's going to cancel each other out. Oh, I almost forgot. I forgot this 2K here, didn't I? Foolish man doing foolish man things. So we have that 2K there as well because the temperature difference of this. So this K is going to cancel out this one. And overall, our units are going to be joules on the top and kilograms. Sorry, joules and then per Kelvin. So our units are going to make sense. It's going to work out as joules per Kelvin. Oops. So how many joules of energy you need to heat the spoon up by 1 Kelvin. So the units are going to make sense. Let's see if the numbers do. So we have 172.655. We're going to times that by 4.05 by 10. But actually, do you know what? I forgot the 10 to the minus 3 here, but it's by 10 to the 3 there, so that you can just get rid of them. 10 to the 3 by 10 to the minus 3 cancel each other out. So we have 1.72655 times 4.05 up the top times 2. And that's divided by the 48. So I got 29.1355. And let's think back to our units. Joules divided by Kelvin. So joules by K to the minus 1, which is the heat capacity of the spoon. So you need to increase the temperature of the spoon by 1 degree Celsius. You have to give it 29.1355 joules of energy. Right, even though the video is quite brief, this took a lot of takes, so I'm going to try and bodge it together. I hope you're well. Remember with these, the key is, first off, the heat lost by one thing is equal to heat gain by the other. Then just be careful about how you go and make sure you use the right values. What I do like is I saw a couple of people started by writing out what they know, like the mass of the milk equals, the temperature at the start equals, which is great, that's a good start. So just be careful, be methodical when it comes to calculations, and just work through it slowly and methodically. Again, practice is the key here. So remember, all of the videos on how to do these are still up there, okay? So I'm kind of rushing through this one, but all the methodical how to do them are still up there, either on YouTube or on our stream account, so make sure to give it a watch. Alright guys, I'll talk to you soon.